So in this video we're going to look at the Brayton process and how it relates to real gas turbines and how real gas turbines differ from the ideal Brayton process. So to begin with the Brayton process, so this is our ideal comparison process for gas turbines, just like the Rankine cycle was the ideal comparison process for steam cycle power plants. And this is very much more simple than the steam cycle. We have only 4 basic components. So if we start from point number 1, we go through the compressor marked with C in isentropic compression. Then we have a heat exchanger where we bring heat to our work fluid. The heated high pressure fluid is expanded isentropically in the turbine. And finally, we do isobaric heat removal, and we are back at point number 1. And if we look at the TS chart, like we did with Rankine cycles and steam power plants earlier, the process looks something like this. So one thing that we can immediately observe here is that, well, 2 things really. One is that there is a significant temperature increase in the compressor. If we remember the Rankine cycle, the pump increased the temperature only a tiny bit. So what that means is that there's going to be a significant power consumption at the compressor as well. The other thing is that because this is gaseous fluid, so we don't have the boiling part. So as we are bringing heat or we are removing heat, temperature is always changing. We don't have this isothermal heat input in boiling or isothermal heat removal in condensation. And as this TS chart is very useful for us to understand the process and understand what affects the efficiency, we'll go through this as well here. So remember from the very first lecture that the definition of heat input when we draw the process in the TS chart is basically the area. So if we do it as a definite integral from beginning of heat input here at point number 2, and then we keep increasing the temperature by bringing more heat, we end up at point number 3. So everything that is under this curve, this graphical area, depicts the heat. And then we did the expansion, and from point 4 here we move the opposite direction to the left, and again everything underneath represents the heat, removed heat in this case. And what that means is that the difference between the added and removed heat when we have ideal isentropic compression and expansion, so we move straight up in compression, straight down in expansion, then everything in between inside of this curve has to be the specific net work. A couple of definitions of terms. So often we're talking about the pressure ratio. So as long as we're talking about the ideal Brayton process with no pressure drops, that means that the pressure ratio has to be the same in the compressor and in the turbine. And we mark that with a lowercase pi and call that ratio the pressure ratio. The other important parameter is the turbine inlet temperature. So we mark that with T tit, and that is in this case the temperature at point 3 where we go into the turbine. Now, speaking of the efficiency, the definition in its basic form is the same basic idea as we had with the Rankine cycle. So thermal efficiency is the net mechanical power divided by heat rate in, or specific work divided by specific heat in. So with enthalpies we can define this as specific network. So it says network here. This means specific network, lowercase w and lowercase specific enthalpies. So enthalpy difference over the turbine, enthalpy here minus enthalpy here, minus the enthalpy difference between 2 and 1, that is the specific network of the compressor. And then we have the difference of these is the specific network of the whole process. And heat input, specific heat input, is the enthalpy difference between point 3 and point 2. So this is where we bring heat into the process. And as we said in the previous slide, the big difference to the Rankine cycle is that the compressor work, we are compressing gas with high volume, high specific volume. That means PV is a large term. That means we do a lot of work in the pump. We have high density liquid. We can get a lot of pressure with fairly little work. And the other observation that we get here is when we look at this process. So if we imagine that we maintain everything else equal and we keep increasing the pressure ratio, the higher the pressure ratio gets, the higher is going to be our efficiency. So basically, the higher this pressure curve, so always in the TS chart as with the HS chart, the higher we go vertically, the higher the pressure is. High pressure isobars are higher up here. And then if we maintain the pressure at turbine exhaust and compressor inlet, then the relative height, so the fatter the process is in TS chart vertically, the better our efficiency. Now, then if we look at the real gas turbine, we have a couple of differences to the ideal Brayton cycle. So one big difference is that we don't have heat exchangers anymore. One of them was completely removed and the heat input heat exchanger was replaced by a combustion chamber. So what this means is that we have here a so-called simple cycle open gas turbine, which is what almost all gas turbines are. I had almost just for the matter of principle, basically we can say that all real gas turbines are like this. So how it works is that our compressor sucks in air from the atmosphere, compresses it to a high pressure. We inject fuel into the pressurized, and because of the pressurization, also now very hot air, fuel ignites, we get to higher temperature, we expand through the turbine, and then we don't cool it in the heat exchanger, but we just exhaust the hot flue gases into the atmosphere. So basically, as with the Brayton process, the compressor is a significant power consumer. Very often more than half of turbine power is spent by the compressor. Very roughly you could say that the ballpark idea of how a gas turbine typically operates is that of all of the fuel heat rate that we put in, 1/3 goes to running the compressor, 1/3 goes to the generator, and 1/3 is exhausted into the atmosphere. So as a rough idea that the magnitudes are broadly similar. And with gas turbines, so these are not Brayton engines, we say that the gas turbine follows the Brayton cycle, or that the Brayton cycle is the ideal comparison process for the gas turbine. So a gas turbine and a Brayton cycle, they are strictly speaking slightly different. Now, if we look at the gas turbine and Brayton in a TS chart, we notice a couple of differences here. So what are going to be the differences? Obviously, our compression and expansion are going to be lossy. Then we have pressure drops. We have pressure drop at the inlet, so there's always some kind of filter so that the compressor doesn't suck in birds and insects and whatnot. There's also, well, because the gas turbine is basically, it works the same way as a jet engine, so it's also as loud as a jet engine, so you have noise cancellation here. That causes pressure drop. Then we go to the combustion chamber. Here is the most significant pressure drop typically, and after the turbine we have the exhaust, so then there's the stack, and this again we have silencers here. They have pressure drop, so we don't get to expand all the way to the atmospheric pressure. And finally we have internal air flows, typically depending on the gas turbine, maybe not in the very smallest ones, but in the larger industrial gas turbines we definitely usually have blade cooling, and that means that not all the air goes through the combustion chamber. Some gets bypassed. We'll look at that a couple of slides later. Then how this looks like in the TS chart, we see it here. So basically pressure drop before the compressor means that we start compressing from slightly lower pressure than the atmosphere, so we have to do more work. Then we have the efficiency of the compressor, so the process bends towards the right, towards higher entropy. We have the heat input. Again, we are sliding down because of the pressure drop. We don't stay on the isobar, we slide down, means that we end up, for a given turbine inlet temperature, we end up further right, higher entropy again. Same thing, bending right on the turbine because of the expansion losses. And finally, we don't expand all the way to the atmospheric pressure because we have to leave something to overcome those pressure drops at the stack and the silencers. So how a real gas turbine looks like, we get an idea if we look at this picture here. So basically, air inlet is on the left side and flue gas exhaust is on the right. In the middle we have the combustion chambers, and we can see that there are many stages of axial compression. So all but the very smallest micro gas turbines have axial compressors, axial flow turbines. And what we notice is that there are a great many more compressor stages than there are turbine stages. So just a couple of stages of turbine, and that makes sense if you think about it. That is much harder to force airflow towards the higher pressure. We can only increase the pressure so much per stage, whereas in the turbine, basically we are going through the natural direction of the flow, so fairly easy to design in a couple of stages, a lot of pressure drop. This is one way of arranging the combustion chambers. In the lecture slides you will see many different types of combustion chamber, but basically this is the, in modern gas turbines, they are always somehow circular around here. They can be annular or canannular like we have here, many different ways, but it's fairly, we are not going to go deep into the construction of those here. Then what kind of performance we can expect from the real gas turbine? So here's just a couple of curves drawn. If we vary the main parameters of a real gas turbine, important parameters are compression and expansion efficiency. So these are now polytropic efficiencies. In the steam turbine we have isentropic. In a different video and later in the lecture slides we will look at the idea of polytropic efficiencies. But now we just know that these are compression and expansion efficiencies, 0.88 typical figures for modern equipment. Turbine inlet temperature could be somewhere from 1200 to 1700 Kelvin, and pressure ratios from 2 to a little bit over 20. It can be higher, actually as much as twice as high in modern gas turbines, but this is what we have drawn here. So we have thermal efficiency and specific power on left and right, and as we increase the pressure ratio, our thermal efficiency goes up to a point, not infinitely as it happened with the Brayton cycle. And if we look at the specific power, we notice the same thing, that we get an increase only up to a point. Now, if we had higher compression and expansion efficiencies, the ideal highest point would move further right towards higher compression ratios, so we would move closer to the ideal Brayton, but this is what we get with typical figures. But we also notice that as we increase turbine inlet temperature, both specific power and thermal efficiency go up basically indefinitely. So what that means is that we basically, as high as we can make the turbine inlet temperature, the better performance we get out of our gas turbine. Then looking at the turbine inlet temperature and what are our limits for increasing that, if that is what we are largely interested in. Basically we have two limitations. One is material strength and the other is thermal nitrogen oxide emissions. So as we know, air is mostly nitrogen. Nitrogen is pretty much inert in most situations, but once we get high enough temperature, it starts to oxidize as well. And gas turbine temperatures tend to be fairly high. So that is one of the reasons why we can't indefinitely increase it. And the other one is obvious, material strength. So basically you can get metals only so hot until you start to have a fairly rapid decrease in the yield strength. So what are the limits? Typically, without blade cooling, we are limited by material strength to below 950 degrees Celsius. With blade cooling, we can get very much higher, several hundred degrees Celsius. Question is, how do we do blade cooling? And the answer is we kind of looked at that already with those internal airflows. So basically, our first turbine stage blades are typically hollow. They have tiny little holes here at the blade, and air comes through the also hollow shaft, comes through here. Our air is going to be at higher pressure because this air did not come through the combustion chamber where we have pressure drops always. So air wants to come out from here, and when the really hot gas comes and this air here forms an insulating film of colder gas around the blade, what it means is that the blade is basically operating in an environment where the temperature is substantially lower than the incoming flue gas stream. So this is a large increase in temperature, and that is achieved by a combination of quite advanced materials and construction, and that means that the first stage turbine blades tend to be extremely expensive, so very often more expensive than their weight in pure platinum. So this is an important parameter, and engineers are spending a lot of effort in trying to find ways to increase the turbine inlet temperature. Now, okay, we can get up to maybe 1500 if you look at jet engines where you can accept a little bit shorter lifetimes, maybe even a little bit higher, but not by much. So how much is our gas temperature going to be? If we burn methane, which is quite common in gas turbines, if we are burning natural gas, even at 25 degrees Celsius, the adiabatic flame temperature is over 2000 degrees. And remember that we are getting air from the compressor several hundred degrees heated already at that point. So we would be way, way higher than what even cooled blades could survive. So how we overcome this is that we put a lot of excess air. So lambda is not 1, but lambda is a very high number. So in a boiler, we typically have something like 1.2, give or take, just a little bit excess air for the purpose of achieving good complete combustion. But here we put a lot of excess air just to be able to cool down the flue gas temperature that will enter the turbine.